Hi, this is John, and today we're going to talk about the last part of memories. Especially, we're going to talk about the flash memories. And for today, we're going to start with the flash memory structure. So as you can see, there's a structure figures of the flash memories, and there's a control gate where we apply a bias to write or read or erase these memories, and there's a oxide called a block oxide, which is to prevent the floating gates prevent to prevent the leakage from floating gate to the current to the control gate. And there's a floating gate, which the floating means the electrically disconnected to the gate or source or drain. And normally we make these gates with heavily doped polysilicon. So this is a simple structure of flash memories. And for now, we're gonna talk about how the flash memory works and how we write or erase those memories. So, as I said before, we apply the bias at the control gate, and when we apply the bias at the control gate, and the oxide thickness will be thinner because of the electric field made by the bias that we applied at the control gate. And then in this picture, the oxide thickness will be thinner, I mean sharper, and the carriers do can move to the next band with the field assist tunneling, which is the foul northern tunneling. I don't know how to say it, but we just call it as a FN tunneling. So if we made these structures, and then and between the two oxides, which is the gate oxide and the block oxide, there's a floating gate, where we put some informations in it. So there's a block like a quantum well. So if we don't apply the bias to the opposite direction, the information, which is the carrier, will still in the floating gate, right? So it works like a well. So there will be no leakage of the carrier or informations to the other side. So that's why we use two oxides to the upper side of the floating gate and the downside of the floating gate. So for now, we're gonna talk how we write some informations to the floating, the flash memories. And for the first, so we're gonna assume that we need we need like the threshold voltage is 5 volt to turn on these flash memories. And when we write some things, when we apply some bias voltage in the which gate? Yeah, control gate. And then we're gonna assume another one that there's a -2 voltage. -2 values of the voltage will be in the floating gate. And so, as I said before, the threshold voltage of the flash memory was 5, and we have -2 voltage in floating gate. So if we wanna turn on, if we wanna make the channel to 5 voltage, which is the threshold voltage, then we have to apply how much voltage? It's 7 voltage because we have 5 threshold voltage and we already have -2 voltage, so we can just add 5 and 2, and which is 7 voltage. So as you can see, the first threshold voltage was 5 volt, but by the floating gate's negative bias, the floating gate's negative charge, it it affects uh, it it affects to the threshold voltage with the screening, because there's a negative charge between the channel and the control gate, so there will be the threshold voltage shift. Yeah, so the first threshold voltage was 5, but the next threshold voltage, which affects by the screening of the negative charge in floating gate, is 7 voltage, so we can say there's a shift in the threshold voltage, right? So for now, so that's the how the write operation works in flash memory, and there's a erase part, and it's really easy. So if we want to erase some information to floating gate at the flash memories, then we can just apply the opposite bias to the gate in the body. So for the NFET, in NFET, when we apply the minus bias, so we can say it's a yeah, when we apply the minus bias, the floating gate's electron will be gone. Will be moved out by the FN tunneling. So that's how we erase some informations in floating gate. So we can see the IDVG curves like this. Yeah, so we have two graphs in here, which is the first threshold voltage and the second threshold voltage, which affected by the screening. So as we assumed before, we're gonna say these threshold voltage, the first graph's threshold voltage is 5 volt, and the second graph's threshold voltage is 7 volt. And when we apply 6 volt in these flash memories, and the 6 volt will be located between the 5 volt and the 7 volt threshold voltage. So when we apply 6 volt in this graph, the current will flow a lot. So we can think when we apply the 6 volt and the current flows a lot, then we're not gonna save the information in the memories. And the second graph, as you can see, the 6 voltage is small. 6 volt is smaller than the 7 volt, the shifted threshold voltage. So the graph, the 6 volt will locate it in here, and the current will not flow. Current does not flow. So we can say the current does not flow, then we will save information in the memories. So that's how flash memory works, and how we save information in the memories, in the flash memories, I mean. And so that's the simple structure and some operations of the flash memories. And for now, for the last part of flash memories, we're going to talk about the advantage and some weaknesses of the flash memories. So the flash memory's biggest advantage is, how do we say this? Integrate integration integrate skills. No, I need to find it. I think we can say it's density, but I want to say it more properly, so I'm gonna search some dictionaries. So degree of integration, yeah, it's the best advantage of the flash memory. So we use flash memories at the mass storage like USBs or SSDs or something. And now we're going to talk about the disadvantages, the weakness of the flash memories, it's the speed, it's the operation speed. Because the flash memories, we have to apply the signal to write the flash memories, and when we apply the bias, when we apply the signal at the control gate, we have to wait until the carriers in the channel move to the floating gate by the FN tunneling. It costs a lot of time. It costs so much time. So this make the flash memory operate way slower than SRAM and DRAM. But in the modern semiconductor industries, or semiconductor, how do I say this? So yeah, in the modern semiconductor, I can say industry is the best thing, but maybe so. In the modern semiconductor industries, the degree of the integration of the device or the chip is the most important part. So still we so still we have a disadvantage of the operation speed, but we still use the flash memories because the degree of the integration is so good. And now, this is the last part of the video. I'm going to talk about the NOR architecture and the NAND architecture very fast, very short. So this is the structure of the NOR part. As you can see, the each transistor is connected with the bit line and the word line. So if we want to if you want to save information one in this cell, in this single cell, then for the first, we're gonna apply the signal at the word line that the signal level can write to write. So when we apply 1 at the word line and we apply 1 at the bit line, then the tunneling will happen and the floating gates, and we can write the information that we want at the floating gate. So as you can see, the NOR architecture's disadvantage is we can address to the single cell, the cell by cell, so we can store the single information to the single cell. And the next one is a NAND. NAND structure looks like this, and we can make a NAND with a heavily doped junction between those gates, like this. Oh, so this is the NOR. This is the NOR structures. How do I say this? This is the NOR structures figure, and this is the NAND structure. And as you can see, there's a metal line connected with the junction. So the NOR structure has a disadvantage of the degree of integration because we have to make junction bigger than the NAND, because we have to put the metal line on the junction. But we don't need metal line in the NAND. So the NAND structure's advantage is the gate pitch is smaller than the NOR junction, so it has the higher degree of integration. But there's a problem. There's a disadvantage. They also have disadvantage in NAND because when we want to read or write the single transistor, then we have to we have to apply signal to the whole transistor. So it will be slower than NOR because in NOR structure we can apply some bias or signal at a single cell, but we have to apply signal all of the transistor in the string structure in NAND architecture. Because of this, the NAND operates way slower than the NOR. And also, when we kept read and write or erase those whole transistors to turn on to program just for the single transistor, then the oxide will be kept stimulated by the bias, so the lifetime of the transistor gets affected. Maybe the oxide has some crack, or it has a defect because of the repeated bias apply. So then the NAND architecture have shorter lifetime. It's the disadvantage of the NAND architecture. So I think this is it. This is my last video assignment of fundamental semiconductor device 2, and that's it. Maybe I will come back. I don't know, but see ya.